Okay, so let's get cooking. All right. Now, I am going to be pivoting a little bit. We're going to kind of finish up our first part of our talk with number conversion stuff today, but I want to start getting into the actual coding stuff a little sooner than I usually would. I know that for most of you, you probably feel like, well, why aren't we already there? But trust me, I've been doing this a while. We're doing it in the right order. But I want to make sure you have enough programming stuff under your belt before I'm gone for those several classes, and we have the guy come in with the quantum computing programming stuff. So I want to make sure you have enough background to not be completely lost during it. Keep in mind, it's not going to require you to be a professional or anything, but I at least want you to have enough tools behind the scenes. So we'll talk about the homework assignment, then I'll show you the conversion from decimal to any other base, and then we're going to jump into the programming stuff, and then we'll hit the rest of the conversion stuff when we get a little bit into the programming, where we write software to actually do the conversion stuff. So we'll hit the learning the details of it then. Okay, so having said that, your assignment today was to look at research the binary, octal, decimal, hexadecimal, things we talked about last class, and come up with why each of those has found their place in computing. Why are they popular in computing? What did we find out? Well, let's start with binary. Binary is the obvious, right? So why do computers like binary? Go ahead. Okay, so digital, on, off, 0, 1. So one thing I want you to have your mind moving towards with any of these bases, and it kind of comes down to changing our mindset of really what numbers are. What are numbers? When I say the number 17, what does that mean to you? Like, you need a little context, right? 17 could be like somebody's jersey number, right? It could be the number of hours that you've been awake in a row, whatever it is, right? So all sorts of different things, but really, what are numbers? They're a way of representing something else, right? So in those two examples, 17 represented some amount. So it was a measurement of an amount of hours, right? What about the number on a jersey? That's not an amount thing. That's just kind of a unique identifier for a person by the back of their jersey for some sport, right? So really, numbers are a representation for some other meaning. They aren't only used for math, right? And even within that, even for math, if we do 5 plus 3 and come up with 8, well, that has meaning too, because what we apply that 8 to might give us some information. Maybe it's again, the number of hours, or, number of miles traveled, whatever it is. So really, numbers is a representation state for something that we're trying to kind of understand, contextualize in whatever problem we're solving. Okay, so I want us to start thinking about numbers as almost the language of numbers. Okay, just like English is this natural language that we use for communicating with other human beings, and programming languages are this language you use for communicating, telling a computer what to do. Numbers are a language for representing either magnitude, if we're using it for size, or maybe kind of uniqueness. We tend to use numbers for like an ID. So if you think about on your ID cards, if you remove the F00 part of it, right, you have a unique identifier here on campus where no two people have the same number. So that uniquely identifies you on campus, right? Where if you just use your last name, there could be multiple people with the same last name. There could be multiple people with the same first name, whatever. That's why we sometimes get the weird emails, right? If you have 3 Mary Smiths, you have Mary Smith 1, Mary Smith, or Mary.Smith 2 at CUW, so on and so forth. And you got to find out, well, which Mary Smith are you when you're sending them an email? So foo numbers are a way of uniquely identifying somebody, and that tends to be something that we use numbers for, because numbers we can count, right? We could say when we assign you an ID, we assign it to you, and then we add 1 to it, and that's your ID. Then we add 1 to it, and that's your ID, so on and so forth. So I want you to start thinking about numbers as a language for representing something. All right. So when we deal with computers and we're dealing with digital logic, which is an on-off, we need to represent 2 different states, right? We need to represent the state of when electricity is flowing through a circuit, on, and when electricity is not flowing through a circuit, off. All right. And then when we talk about the actual hardware inside of our computers, which we'll look at in the 325 class that you'll take next semester, what you run into is in between, these digital circuits, they're built up using these various logic gates. And, we already talked about processors. Processors have a whole bunch of magic tricks on them. So you have your input coming in one side, electricity. You have your output on the other side, electricity. And in between, we got a bunch of magic tricks, right? Some of them are physical magic tricks. When we start writing software, we're augmenting those physical things with software-based things. But electricity is flowing through these AND gates and OR gates and all sorts of different magic tricky type gates, ultimately turning electricity on and off, or, all sorts of different things, giving you an output. All right. So at the end of the day, when we're dealing with digital logic, digital computers, we need to represent 2 different states, an on state and an off state. So we really only need 2 unique values. So binary base 2 works perfectly well, right? All right. So that's why we use binary when we're, that's the reason we use binary with computing. All right. Let's do the obvious, decimal. Why is decimal part of what we do in computing? Go ahead. All right, because we're involved, right? So this whole thing, the whole reason you're in computer science here is because you want to leverage this guy here to make money, right? And we already decided we're not going to drop down to the 0 and 1 level. So we want to operate as close to our normal human level as possible. And we have 10 fingers, 10 toes. So we like decimal. We're used to that decimal numbering system. So since we're involved in the computing equation, we're going to have decimals involved because we're sometimes looking at it. Okay. So those are the obvious ones. One's the language of computers. One's the language of people. Okay. Now let's look at the other guys. So octal. Octal is actually probably the hardest one to conceptualize. So let's talk about that one next. So why is octal used in computing? Go ahead. Okay. And actually, you could use a very similar argument to that for at least part of why hexadecimal is popular. So last time we were looking at some conversion stuff. And today we're going to look at the conversion stuff on the other side. Okay, we're going to look at that here in a second. But it specifically, octal, which is base 8, which is a power of 2. 2 times 2 is 4, times 2 is 8, right? So since it's a power of 2, you're going to start noticing that as a pattern in computing. Powers of 2 tend to be related to computing. Whenever you get a computer with memory, the amount of memory you have is a power of 2. It's a multiple of 2. All right. So in any case, octal, without giving you an example at the exact moment, converts very easily directly between octal and binary without having to go to decimal in the middle. Okay, we're going to see that here in a few minutes, because our normal cadence, if we want to go from octal to decimal, our normal cadence, if we want to go from octal to binary, we go octal to decimal, then decimal to binary. Like a 2-step process if we're doing the math problem to solve it and showing our work and all that stuff. But the reality is, for a couple of our bases, base 8 being one of them, you can go directly from octal to binary very conveniently. You don't have to make a pit stop at decimal. And that same thing is true with hexadecimal, base 16. All right, so that's a rationale for why we're using base 8 instead of like base 7 or base 9, right? Because those don't allow you to do that direct conversion, and I'll explain why. But for right now, we don't have the context for it. But just trust me, base 8 maps directly to binary super easily. You mentioned it's like 3 bits. So just like we learned last time with base 8, what are the legal, they're called octets, what we're dealing with. So with binary, it's the bits. We have 0 and 1 for base 2. The bits are 0 and 1. For decimal, our digits are 0 to 9. So what are the legal octets for base 8? 0 to 7. All right, 0 to 7. Now, I'll just show you really quick here. I think this was one. Octal binary map. This is a 0. This is a 1. This is a 2, 3, 4, 5, 6, 7. So you just finished telling me that the legal octets in octal are 0 to 7, and we can use 3 bits to represent 0 to 7 fully. Over here on the left, this is every permutation of 3 bits. I'm using them. I haven't left any of them out, right? So we can fully map the octal, the octets 0 through 7, using exactly 3 bits. And guess what? You can completely represent the base 16, the hextets 0 to 15, so 0 to 9, A through F, using 4 bits. Okay, exact same thing, just the slide will be a little bigger, right? Because I'll need to have, you'll have 0, 0, 0, 0, 0, 0, 0, 1, blah, 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 all the way to 1, 1, 1, 1. Okay, so octal is a nice intermediate step because we can fully represent all the octets in 3 bits. And it's important that we're saying, because again, I want you to think about these numbering systems as a language. If we use 9 bits, or if let's say we use base 9 instead of base 8. Okay, so instead of octal, we use base 9. Well, base 9 allows the numbers 0 to 8, right? Well, we can't represent that with 3 bits because we see that we run out of every permutation of 3 bits at 8 unique representations, right? There is 8 unique ways to write 3 zeros and 1s next to each other. That makes sense? Which just happens to be exactly the number of things we need to represent for the octal number system. We need 8 unique representations for 0 through 7. Now, if we're dealing with base 9, now we need 0 to 8. We need 9 unique representations. We can't do that with 3 bits. Can we do it with 4 bits? Sure. But 4 bits, we're not using every unique representation. We have some leftover stuff that were, leftover permutations of 4 bits that we didn't use to represent the numbers 0 to 8. Make sense? Okay. That becomes a problem when we do our mappings. And that'll make sense later when we do our conversion. A few minutes ago, I mentioned that with octal, we can go directly from octal to binary without stopping at decimal. With hexadecimal, we can go directly from hexadecimal to binary without stopping at decimal. Make sense? All right. With base 9, we can't do that. Base 9, we'd have to take the base 9 number, convert it to decimal first, then we can convert that to binary. Still get the right answer. You know, we get the conversion, but there's an extra step there, especially if you're having to do the math on your on an exam or something, and you're going to show your work. Now you're basically solving two conversion problems. You're going from base 9 to base 10. Then you're going from base 10 to base 2. Two separate conversion problems using our two patterns. Not the end of the world, but if we're thinking about computers and we're thinking we want these things to be fast, the compatible bases seem to make more sense, and octal is one of those. Okay. Now, specifically, one of the things anybody find in their research, one of the things that the octal numbering system is used for specifically on computers. Go ahead. Okay, that actually is true. That not what I was thinking. What else?
Used for file permission.
Yeah, that's kind of the famous one. If you ever used a Unix or a Linux operating system, well, if you've been on Windows, you've seen this at a button click level, right? Some files are read only, some files are read write. So a file could be write only, although that's not a real common thing, right? Typically, what we experience as users is you could have a file that's read only, which means you can't change it. Right? You've gotten those Word documents before that say, you know, you can't change this file. You got to create a duplicate of it first if you want to make changes to it. So that was a read-only file. You could have a read-write file, which is our common thing where, hey, I can read it, but I can also make changes and save it. So that's read-write. And then we also have files on our computers that are executable. Okay. That means you double click on it and something, a program runs or something. So those are kind of three different states: write, read, executable. And then we have the combination of all those things in between. We represent those as 3 bits. And there's a famous command in Unix called chmod, change mode, where you can change the mode of a file to be, you know, for instance, if you want it to be read, write, and execute, you would do chmod 777, then the name of the file. Okay. And that's read, write, execute for the owner of it, and then read and execute for the group, and read and execute for everyone else. So only a person who owns the file could write to it. Okay, the details of that don't really matter, but the punchline here is that octal is very compatible with that idea. Okay, we already said it's compatible with the mapping between base 8 and base 2. And whenever we're dealing with computers, base 2 is probably going to be involved, right? Okay. But it also happens to play right into that idea of file permissions that are dealing with, you know, 3 different states of a file permission for 3 different groups of users: the owner, the group the owner's in, and then everyone else. Okay. Not something I'm going to test you on, but just kind of that's a use of octal, common use, but there's plenty of other uses as well. All right, so what about hexadecimal? Why is hexadecimal popular in computers, other than it also has that mapping thing? With 4 bits, we can fully map all of the hextets of the hexadecimal numbering system. So 0 all the way up to 15. 0, 0, 0, 0 is 0. 1, 1, 1, 1 is 15. So we can represent, or F, we're speaking hexadecimal. So we could fully represent the entire collection of hextets with exactly 4 bits, which means it allows us to quickly map between those two. All right. So outside of that, what's the other reason why hexadecimal is a popular base for computers? Go ahead.
It can be used in assembly language, but it's used for programmers to read.
Okay. Probably not really easier. Computers like the binary, humans like the decimal, but you're right. It does exist in assembly language because that almost exists for us to scare ourselves, right? Assembly language is supposed to seem intimidating and talk you out of computer science, and that's why we have these power tools for the people who stick around. So probably not really easier for anyone actually involved. but it is in assembly language. There's a more obvious connection. Go ahead.
More compact and like representation of binary.
Yeah. So let me adjust that a little bit, but you're right where it needs to be. So really, it's a way of representing large values in a more compact footprint. So, and if going along with what you said, the least compact way of representing large values would be binary, right? So if so for instance, and places like Best Buy used to do this. You would go into Best Buy, you were looking at a computer, and it would tell you how big the hard drive was in the computer. And it would give you the number, the hard drive size in the number of billions of bits, right? You know, this is a, 750 billion bit hard drive, which bigger number means bigger capacity to a human being, right? Because most of us are not sitting there speaking bits and bytes and yada, yada, yada. All right. So it seemed like a really big number. So it seemed like it was impressive. So you were buying a really large capacity. But if you were to convert that big, long binary number into a smaller footprint, you were to convert that binary number into hexadecimal, you would end up with a much more compact representation of the exact same value, right? Same magnitude, just represented using the hexadecimal language of numbers rather than the binary number. So if we think of binary as our most inefficient way of storing a large magnitude, hexadecimal is far more efficient in that from a human being perspective, we'd rather look at something like that rather than something like this. Make sense? So it's a convenient way of representing large numbers, which then could also translate to what you said, maybe in a assembly language, you might want to represent a value in hexadecimal as opposed to binary. Most of our assemblers today will let you represent values in decimal, because human beings even complained about the hexadecimal side of things, but these are all truths. So really, at the end of the day, hexadecimal has two things going for it. It has easy to convert between binary and hex, because it's got that magic trick thing where 4 bits let you fully explore the what I usually refer to as the bit space of hexadecimal. So all 16 representations of the hexadecimal values 0 through 9, A through F, can be fully represented with exactly 4 bits. But it also gives us a way of more condensedly representing what typically ends up being big values. All right. So as an example, those of you who are sitting here with laptops, you have computers back in your dorms or whatever. How many of you have a hard drive that is at least 1 terabyte? Whatever that means, whatever 1 terabyte means. Okay, 2 terabytes. Okay, anything bigger than 2 terabytes today, your hard drive's now slower, right? So if you have like a console and you get one of those hard drives that are 8 or 16 terabytes, those are based on older mechanical hard drive technology rather than solid state. We like solid state stuff because it's faster and less moving parts. So if we drop our laptop, it doesn't break. All right, but right now 2 terabytes is kind of where our wall is for how big our no moving parts hard drives are. Okay, but 2 terabytes, if we were to write that differently, let's say we were to write that in terms of bits. So size conversions. And I'm gonna hit this pretty quick. And then we're going to talk about it in more details later on when we go to write a program to do the conversions, because I want to get us into the code as soon as possible. All right, so we have the bit side of things and we have the byte side of things. So we have 1 bit. This is a 0 or a 1. Okay, we have 1 kilobit, small k. Okay. Actually, it's small k, small b is usually the comparison. You can usually tell the difference actually on the b. So a bit has a lowercase b, a byte uses an uppercase b. So 1 kilobit is 1024, not 1,000. It's 1,024, which by the way is a power of 2. 1,024 bits. 1 megabit is 1,024 kilobits. 1 gigabit is 1,024 megabits. 1 terabit, which nobody really uses that, is 1,024 gigabits. We go over to this side, we have 1 byte is equal to 8 bits. So we notice as we go down our list here, everything's a scalar of 1,024. Multiply 1 by 1,024 to get kilobits, times 1,024 to get megabits, times 1,024 to get gigabits, times 1,024 to get terabits. When we jump to the byte column, we first need to multiply by 8. So 1 byte is 8 of these guys. Then we have 1 kilobyte is 1,024 bytes. 1 megabyte is 1,024 kilobytes. 1 gigabyte is equal to 1,024 megabytes. 1 terabyte is equal to 1,024 gigabytes. Okay, so for those of you who have 2 terabyte hard drives, your hard drive is actually a 2048 megabyte hard drive. Times 1,024, they could give it in kilobytes. Times 1,024 could give it in bytes. So if you want to go off of that, so we have 2 terabytes times 1,024, that's megabytes, times 1,024, that's kilobytes, times 1,024, that's bytes, times 8. That's the number of bits. So if you walk into Best Buy and they have 17,179,869,184 bit hard drive, that sounds like a bigger hard drive than a 2 terabyte hard drive, even though it's the same number. Make some sense? So that's that example of how hexadecimal, well, this is a starting point. That's an example how we like a more compact way of representing large values. Okay? So we can accomplish that through different multipliers of bits using this thing here. And this is actually a popular bait and switch thing that most of you have probably run into if you've ever had to buy your own internet. Yeah, so when you get internet, now they have, you can get gigabit internet at home, but if we go before gigabit, a lot of people who have gigabit internet assume they're getting this, but they're not. They're on this side of the coin. Same thing with megabit. So for instance, kind of your baseline, if you have cable modem service, your baseline is like maybe 200 megabit per second internet, not megabyte per second, it's megabit per second. So 200 megabit divided by 8 is actually a maximum theoretical speed of 24 megabytes per second. That's the maximum download speed you can get, as long as whoever you're downloading from can serve it to you that fast. This is more of a networking discussion, but understand that the commercials, when you're buying internet, they're selling it to you as either megabits per second, or just more recently now they say, oh, it's gigabit internet. But the commercials have stopped calling it that. Now they call it, oh, it's 200 meg internet, or it's 1 gig, or it's gig internet. They leave some of the details out of it, so you think you're getting 1,024 megabytes per second if you are on gigabit internet, when you're actually getting 128 megabytes per second. That's the actual speed, because you have to jump over to the byte column. Got a question over here?
On Xbox, like in console, they have they download in, I think, megabyte. But on computers, they download in megabit.
The speed you're seeing it download at, they convert to megabyte, because that's what we like. Okay. So if you have gigabit internet at home, and let's just say you're downloading from some, like Google or something that can serve it to you at gigabit speeds, the fastest speed you'll ever see, but usually it does give it to you in something like, oh, you're getting this at 68 megabytes per second. Okay, it doesn't give it to you in gigabits or megabits. Okay, because we understand the idea of megabytes or gigabytes. Computer scientists should understand it even better, but the average consumer, download speeds historically, when we had dial-up modems, we looked at download speeds in terms of kilobytes per second. Okay, but if you think back, I know most of you weren't alive then, but the fastest dial-up modems were 56K modems. You've heard of a 56K modem before, even in a history book. That was 56 kilobits per second. 56 divided by 8, that's only 7 kilobytes per second. So the fastest dial-up modem that ever existed, your download speed was 7 kilobytes per second. If you want to put that into your Xbox download speed, that is 0.0068 megabytes per second. So your 130 gigabyte game gonna take a few minutes. Probably we can do the math, but months, right? So our internet speeds have had to get quicker and quicker and quicker as our file sizes have had to get larger and larger and larger because human beings are greedy. Okay, as soon as our internet speeds get faster, oh, we want higher end graphics, right? We want, games we used to be happy with. What if Super Mario Brothers 3 came out today? Oh, it would flop. Yeah, by today's standards, Super Mario Brothers 3 was junk. But by those days' standards, it was a game that was back when video games were cool. Super Mario Brothers 3 was announced in a movie called The Wizard. It was they made the unveiling of that game in the last sequence of a motion picture. They don't do that anymore. Right now, it's on the internet. You don't have to go to the store to buy it. You just download it. All right. So in any case, these are our size conversions from bits to bytes to kilobytes, yada, yada, yada. I'm going to hit this again at some point. I know I'm kind of glossing through this stuff. There will be conversion questions on exams, but I'll make sure we cover it in a little more depth, more practice before we get to that. Again, I just want to get us to the coding stuff as quickly as possible, but hopefully this at least gives you some context. Okay, when you buy internet, for example, you're buying a number of megabits per second, small b. But when you measure your download speed, you're seeing it in megabytes per second because that's something we're more familiar with. But the average consumer thinks those are the same thing. That when you're buying 200 megabit per second internet, you translate that in your head as an uneducated consumer as 200 megabytes per second, even though that's not what you're getting. Getting 25 megabytes per second is the reality. Okay, gigabit is not 1,024 megabytes. It's 128 megabytes. Okay. There's your conversion. To jump between columns, it's a scalar of 8. So if I want to go from bits over to bytes, I got to divide by 8. So gigabit is 1,024 megabits. Divided by 8 is 128 megabytes. Make sense? So to recreate this chart, for instance, if you ever had to do a conversion question, you really only need to know 2 things. The number 1,024 and the number 8. That lets you do your jump. Lets you go between any of those things. You probably need to know the names of things: bits, kilobits, megabits, gigabits, terabits. After that, you get into things like exabits, but we haven't gotten into using those yet. And this kind of brings our conversation back to the hexadecimal thing. So we mentioned that one of the reasons that hexadecimal is a popular computing number is A, it's convenient to convert between binary and hex directly. You can use 4 bits to represent all of the hextets. But it also has the advantage of allowing us to represent large values in a smaller footprint. It's like a compression type thing, right? We just saw some gigantic number of bits, like a 2 terabyte hard drive was this 17 billion bit hard drive. That's a big number, right? All right. But the reality is you can say that same value is 2 terabytes. So we like compressing things down to smaller sizes. It's convenient. Great. Well, after 16, base 16, the next size would be base 32. And we can still accommodate that with our alphabet. All right. So we can accommodate up to base 36. Because we have 26 letters of the alphabet, and then we have 0 through 9, 10 unique ways of representing those first values. So that's up to base 36 that we can accommodate with the English alphabet. After that, we have to get a little bit unique, maybe using upper and lowercase letters, but whatever. This will make more sense maybe later on. But in any case, technically, without changing alphabets, we could upgrade from base 16 to base 32 and still have that fast conversion, because you can represent all the values of base 32, 0 through 9, and A through whatever the 22nd letter of the alphabet is. You can represent all those values with exactly 5 bits. You could fully represent a base 32 number using exactly 5 binary bits. So you can still do that quick conversion. So why don't we? Why haven't we gone to base 32? Why are we still stuck at base 16? Because base 32 would allow us to squish down our values even more, right? If base 16 can turn a giant number like 17 billion into a 2, right? Why, if base 32 potentially could get certain values even in a smaller footprint, why haven't we done that? What do you think? Go ahead. Yeah, really, base 16 at this point allows us to represent the values that are possible in computing today in a small footprint. We haven't run out of those numbers. Maybe once we get to some zillions and zillions of terabytes, we might need to go back and say, okay, well, now even our hexadecimal values are getting a little bit big. Because one of the main places we see hexadecimal values, let me ask this first. So in computing, in your research, where did you find is one of the main places you see hexadecimal values? Go ahead. Memory addresses. All right. So, and we're going to get into this with programming stuff reasonably quickly. One of the first things that will scare you away from computer programming is a memory address, because they're scary looking things. It's like a 14 character hexadecimal value, which seems intimidating to us, right? Wow, I don't want to show you an example because that would take some time, but in any case, it'll be like, a big long number, but written in hexadecimal, and hexadecimal is uncomfortable for us, right? Because we like decimal numbers. That's our comfort zone. Binary is uncomfortable because it's just a whole bunch of zeros and ones. We don't really know what that means. And hexadecimal, even though it's a smaller physical size value, it's still uncomfortable because we're used to base 10, right? It's really not substantially different than if you are over in Europe and you're looking at the speed limit signs and all of them are in kilometers per hour instead of miles per hour, right? We can sort of kind of maybe get an idea of that conversion, but that's not comfortable for us either. Okay, well, for humans who are also Americans using our numbering system, right? Kilometers per hour is a little bit different value, because it's representing, meters instead of some baseline of miles. Okay, so we really don't need to go bigger values yet, but memory addresses are an intimidating part of computing for really no good reason. This kind of goes back to how first day of class I talked about that human beings are so good at solving problems that we sometimes have trouble articulating how we solve them, and that's actually the challenge of becoming a good computer programmer. is you have to train your mind to be the translator between how human beings solve problems and how this guy needs me to represent solutions to it. Okay. Now, with that in mind, in real life, all of you know your home address, right? All right. Now, when we think about human-based addresses, there's a lot of parts, right? 123 Elm Street. Then you have a town, a state, a zip code, and now they've added those extra 4 digits to the zip code for I don't know, weird reasons, I guess, but gets it to the right local post office and that kind of stuff. But in any case, human addresses are quite complicated. There's lots of parts, right? And that's just to get us to a place here in the United States, right? You start looking at addresses over in overseas. Now now you have to throw in the country that you're traveling to. Okay. Now we do have the alien civilization here in Cedarburg. Anybody here live in Cedarburg or have seen Cedarburg addresses? Yeah, they're nonsensical addresses. So, it's like NSW. You might as well just be given GPS locations to the thing. But Cedarburg likes to be special, so it is what it is. But so outside of Cedarburg, Wisconsin, our addresses are typically something like 1, 2, 3. So a house number, a street, a town, a zip code, a state, a country. So lots of things that we use to uniquely identify a single place on Earth, right? Yet we're not intimidated by that. Why? Because we've been using it our whole life. As a kindergarten or first grade, you had to memorize your home address. You had to know your number, your home address, those things. Otherwise, they don't let you leave school. I assume they still do that, or they just assume you know it. Or it's just in your phone. Like, I actually don't know my address, but it's in my phone, and my GPS can take me there because I click on the button that says "Take me home." So that's become a real thing, I guess. But in any case, human versions of addresses are far more complicated than memory addresses in a computer. So when you buy a computer and it comes with 16 gigabytes of memory or 32 gigabytes of memory, or 64 gigabytes of memory, whatever that is, on a computer, if you want to think about each memory address as a plot of land for a house, there's one gigantic street. Everybody is on the same street. Everybody's in the same town. Everybody's in the same zip code. Everybody's at the same state, country, yada, yada, yada. There is one really, really long street with house number 0, house 1, house 2, house 3, house 4, house blah, 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 all the way down the line to represent 16 gigabytes worth of unique addresses. And depending on how big an address is on that particular operating system, that tells you how many unique houses there can be on that street. But let's just, keep it simple for us and say there's a lot. All right. So if we were representing that final house, if we even just use it as bytes, we would say something like, well, here, I'll just keep it generic. We would say something like, oh, the final house down at the very end of the street is house number 17 billion, something like that, which as a human being is a good size number, right? Now, if we were counting in binary, that's that house number, right? Still means the same thing. It's just the binary representation of 17 billion instead of the decimal version of 17 billion. But now hexadecimal allows us to represent it like this. It's a more palatable number, but it's scary looking, right? It'd be less scary looking for us if it was a little bit longer, but still in decimal, because we know how to read decimal numbers, right? But then you got to do the math. Like for us, we can pretty much go into like the hundreds of thousands for a decimal number while we can just glance at it and say the number. But once you get bigger than that, you have to kind of figure out your groupings of 3 and decide, okay, am I at billions or millions or trillions or, quadrillions? Where am I? Where am I in terms of saying that number out loud? All right. So the idea is computers use hexadecimal values to represent each individual house on the street, memory address in the computer. but it's a far simpler address model than human beings use. Everybody lives on the same street. Make sense? Right? But the reason why people get intimidated by it is because it looks scary. And I promise you, when we start talking about things called pointers, when we in C++, and we start looking at things that are memory addresses, you're going to be uncomfortable, even though I just explained that it's actually a far simpler model than our addressing in real life, your house address. Makes sense? We can uniquely identify a place in memory on your computer by a single number. Which bucket of memory, which house number is it on this one big long street? Make some sense? All right, so hexadecimal allows us to do that. I asked, well, why haven't we gone on to whatever base 32 is called? It probably has a mathy name. I don't know what it is, but whatever base 32 is called, why haven't we gone on to that? Well, because we really haven't run into the situation where we have to compress it that much further. Now, there has been a real life example that, whether you're aware of it or not, we have started running out of large numbers. When I say IPv4 versus IPv6, does that mean anything to anybody? Just throw a slide up here. IPv4 versus IPv6 network systems. And so the old system was IPv4. Now we have IPv6. Why did we need an upgraded numbering system? In our computer networks, every one of your computers that's on Wi-Fi right now has a address. And in computers, it's called an IP address that uniquely identifies you depending on the type of network you're on. I'm not going to go too far into this because it's more of a networking concept, but you have a unique thing, a unique number that identifies your computer on whatever network you're on. Here on campus, if you have a 172 dot something number, let's see what I got right now. Yeah, right now I have a 172 number. That's what's called a real routable IP address. Okay, so that actually is a number that is unique on the internet, but because I'm here on campus and we have something on campus called an edge router that protects my computer from getting bombarded from off-campus stuff. People can't hit my computer from out there. But if you've ever been on or at home, you see your IP address is something like 192.168. something or 10. something. Those are what are called non-routable IP addresses, which ultimately means they're only uniquely identifying your computer in your house on the network you're on. Okay, but the bigger problem, this IPv4 versus IPv6 thing, is in the very early days of computer networks, before we were convinced that we were going to have 4 zillion computers on the internet, they handed out blocks of IP addresses to different organizations like Concordia, like Northwestern Mutual, whatever. And they said, oh, here's your little section of 6,000 IP addresses. Even though at any point in time, those places might only be using, I don't know, I'm just making up numbers at this point, 1,000 of those. That means we've wasted 5,000 IP addresses that technically Concordia has been handed that they've never put to use, because on campus here, we have a couple different networks where we don't even use those internet-wide unique addresses. But bottom line is, they've handed out enough IP addresses that somebody owns that we actually, and then you're going to consider the number of computers that are actually connected to the internet that need to be uniquely identified. We've run out of IP addresses, right? We no longer can represent as many unique computers. And wouldn't you agree that probably the number of computers that live on the internet today, one way or another, is probably a lot larger than what they ever would have imagined it would have gotten to day 2 of the internet? Yeah, it's kind of become a thing, right? So IPv6, what it does is it kind of makes that jump. Kind of like the jump from base 16 to base 32. It gives us more unique addresses. That will probably run out of those too, right? But we're just buying us time. That's the human way. We kick the can down the road, right? So we'll just say ran out of IP addresses. All right. So let's see. So that pretty much gets us through the homework. We kind of have a decent idea on why there's these different bases and why we've chosen those certain ones. There's nothing really special about base 8 versus base 9 other than its compatibility with binary. There's nothing really special about base 16 versus base 15 or base 17, except its compatibility with binary. Similarly, there's nothing special about base 32 versus base 31 or base 33, except its compatibility with binary. Okay. So we just started talking about memory. So, and this kind of is related to the story, and I'm trying to figure out what things can I leave out right now, but this stuff is kind of important for us to give us our baseline. So let me try to get through this stuff in the 20 minutes, and so we can start with coding next class, and then get rolling. All right, because this really does tell that foundational story, and I will fill in the other things as we go. I just need to get you where I need you to be for the quantum programming stuff. So computer memory, whether we're talking about hard drive size, or we're talking about your 16 gigabytes of memory, 32 gigabytes of memory, 8 gigabytes of memory, whatever it is, memory used to be very expensive. How many of you have heard of the Y2K bug? Anybody know what the Y2K bug is other than just the name? Go ahead. Okay. And why were they concerned that it was going to stop working? Okay. So in the year 2000, I remember sitting on my couch watching. It was the first time I've ever watched, as the clock hits midnight at every single country around the world. It was televised everywhere just to see what was happening. Where was the world going to explode or whatever? It was really entertaining. But in any case, memory used to be really, really, really expensive. I'm going to show you an example of that here in a second. So because of that, early software programs used a 2-digit representation of a year rather than a 4-digit representation of a year, which means that the year 2000 is the same as the year 1900. Make sense? In a 2-digit representation. So now they're like, oh no, what things are going to break because of this with now all of a sudden you have people that are like negative 71 years old and stuff like that. Things get kind of, I guess, kind of weird, whatever. So there was this kind of worldwide upgrade thing where they went and updated all these pieces of software to use 4-digit dates rather than 2-digit dates. Okay. The reason they had chosen 2-digit dates years ago is because computer memory was not very big and was really expensive per, let's just say, per bit. Now that we know what bits and bytes and all these things were, it was really, really, really expensive. So we wanted to be very careful of how we spent that relatively low amount of memory. We didn't want to store things that we didn't have to store. So the way we think about computer programming today is much more convenient because now we don't really worry about that. Memory is cheap. And so we're going to say use 2-digit years instead of 4 because memory was expensive. Now let me give you an example. All right, so anybody in here build a computer relatively recently with some memory? We got how much memory? Okay, that's your hard drive. System memory, 16 gig, 32 gig, 16 gigabytes. Okay. So your 16 gigabyte chip, you probably bought 2 8s, is my guess. Yeah. Yep. So how much did each of those 8 gigabyte chips cost roughly?
I bought a 2 pack.
Okay, so call it $80. We'll inflate it. right? So we'll call it $80 for 16 gigabytes of memory. So $80 per 16 gigabytes, big B, of, when I say memory, we're talking RAM, random access memory in your computer. We have the first thing you gave me, the 2 terabytes, that's his hard drive size. That's long-term storage versus short-term storage. Short-term storage is smaller but faster. Long-term storage is larger but slower. Okay. And then there's all sorts of levels outside of that too for different kinds of memory on your system. All right, so today's rate, we're going to say 16 gigabytes to cost $80. Okay. Now, 16 gigabytes by today's standards is a pretty good amount of memory. Not budget pleaser, but there are computers with more memory in it than that. Okay, but 16 gigabytes, if you bought a computer today that had 16 gigabytes of memory in it, it's probably more memory than you'll ever need for the lifetime of that computer. Your next computer will probably have more memory in it, but for right now, 16 gigabytes is plenty unless you're doing very specific things. My computer has 96 gigs of memory in it here, but I do a lot of virtualizations. I think I've shown you before. I run full operating systems on here. So here's Windows 11 running on this computer, so that uses up system resources. So it's not that my Mac operating system is requiring 96 gigs of RAM. You know, I probably never use more than between 7 and 10 gigs of RAM at any one period of time on the Mac OS. Okay. So you don't need more than 16 unless you want to carry around a single machine and be able to run a whole bunch of different simultaneous operating systems on it, which is something that in my profession, I have to do, or I have to carry multiple machines. And as you get older, you become you become weaker, and then you get back problems. You don't want to carry extra stuff. All right. So in any case, when I was trying to think of the age, well, so 1996. So this is in the year 2023. So in 1996, how much memory do you think was a kind of equivalent to 16 gigabytes of memory in a computer? What was a good amount of memory for a computer in 1996? What would you guess? Go ahead.
8 megabytes.
8 megabytes. You look it up?
No, I have it from notes. I watched you.
Oh, okay. Okay. So don't give too much away then. Okay. So in 1996, I had a computer that came with 8 megabytes of memory. Now I wanted to be the cool kid, and I wanted to double the memory to 16 megabytes. All right. So that means I needed to go out and buy 8 megabytes of memory, similar to how he bought 16 gigabytes of memory. Now, just so we're dealing with the same numbers here, let's go ahead and take what we learned today, realizing I went through it fairly quickly, and let's convert 16 gigabytes to megabytes. So that's 16 times 1,024. So that's 16,384. So that's 16,384 megabytes. $16,384 divided by 8. So really what we're talking about here is 2,048 times the amount of memory that he purchased compared to what I was purchasing. Okay. He paid $80 for 2,000 times more memory than I bought in 1996. In 1996, how much do you think 8 megabytes of memory cost me? $3? $300? Keep going. Go ahead. $1,000.
No, that wouldn't have been a computer.
Oh, no, but here's the kicker. Memory had already started coming down in price. This was considered cheaper. Really famous guy, I'm sure you haven't heard of, Bill Gates. How many of you heard of Bill Gates? Microsoft dude, right? He had a famous quote one time that says, "Oh, you'll never need more than 32K." He meant 32 kilobytes. You never need more than 32K of memory. Well, I don't know. He bought 16 gigs of memory. Okay, now he's regretting it. He's like, well, Lippmann has 96, and it's a Mac. It's you have 32 on your Mac? Oh, so he's smart. Future. Well,
like 4 years ago, I got 8.
Yeah, well, but Macs, as Apple does, they force you into this, right? Because it's not upgradable. So when you buy this Mac, this thing is cryogenically sealed or hermetically sealed, where you need to buy everything you ever wanted day one because you're not putting anything extra in here. It's part of why they kind of work, because everything's on a single chip, but at the same time, it's not user upgradable. So, once your battery is shot, it's expensive to replace. Once your memory, you need more memory, you gotta buy a new laptop, so on and so forth. All right, but in 1996, I spent $1,000 for 8 megabytes. So let's just look at the thing. So 1,000 divided by 8 is $125 per megabyte, as opposed to 16,384. And we're going to divide that by $80. So that is zero. Oh, we're going to do 80 divided by that. So that's 0.00, let's just say 005. 0.005 dollars per megabyte. All right, so 125 divided by 0.005 is 25,000. So that means memory today is roughly 25,000 times cheaper than it was in 1996, when it had already come down in price. Does the whole Y2K problem kind of make some more sense now? We had less memory total anyways. We hadn't come up with the manufacturing ability to create as much memory. Not that anybody could afford it, right? If we go off of the standard back then, if he had 16,384 times 125, that is $2 million. You got that just laying around? For his RAM. His 16 gigabytes of RAM was $2 million, not $80. He went on one of Amazon's great payment plans, right? Locked in for life. And again, it had already come down in price. He was getting a deal. All right, so that's where the Y2K problem came from. And people who don't understand that backstory there might say, oh, well, these were just idiot programmers that were like, why did they represent it as two digits rather than one, or rather than 4, rather. Keep in mind that 2 digits, decimal values, requires more bits than that to represent it, right? So now to find out what the actual footprint is, you would have to convert and find out, well, in order to fit that many things, writing it as bits, now I'm taking up storage. That kind of tells you how much storage you're taking up. Bottom line is we had less storage and it was super, super expensive. So you either pay more money or you find ways to store what you need to store in a smaller footprint, i.e. 2-digit years instead of 4-digit years. And we'll just hope that, well, either we don't make it to the year 2000 or something has replaced us. That was probably more of the mindset, is that, oh, this is a temporary solution. There's going to be something better that's going to fully replace this before 2000 anyways. All right. Okay, but here you're seeing that difference in cost when it had already come down in price. And we wouldn't be building gaming PCs today if just the RAM was $2 million. Okay, because his budget for his entire computer was probably, depending on his graphics card, everything but the graphics card, I bet you his budget was probably in the $500 to $600 range. Then he gets to decide, okay, well, how much am I willing to trade my soul for to get my graphics card? And that's how he picks his GPU. He can get probably a good enough graphics card for a couple $100 all the way up to a couple $1,000 for a graphics card. And then you might decide, well, we go overkill and we're going to get 2 or 4 of those graphics cards and we're going to link them all together to, and then mine. Well, now that's changed. Crypto is no longer, at least the popular mining crypto is no longer proof of work. Now it's proof of stake. So that's why all those graphics cards are now available. Yeah, for about 7 years, you couldn't get a graphics card.
I got a 1070 and it was like $500.
Yep. All right. So we have an appreciation for use of memory. So if we roll back and we put ourselves as a C++ programmer in the early days of normal computer programmers, what we would call a computer programmer today, somebody sitting down at a physical computer, writing software, compiling it, testing it, that kind of stuff. Before that, we had these things called punch cards, where you wrote your program by punching out these little holes, and you had to take a stack of these cards up to something that processed it. And then when you find out you had a bug, you went back and you had to redo it. So it wasn't efficient. So we had this giant jump forward in the ability to do things. And I think I had mentioned the Malcolm Gladwell books at some point in here with something called Outliers. Bill Gates is, did I mention this? Did I talk about Gladwell books? All right. So Bill Gates, his thing was he was like your age when that was that translation, a little bit younger than you, but when we went to having computers that you could program directly on the computer. And they had a rich founder, a rich booster for his high school, where they brought a computer in and told these kids to, hey, teach me how to use this. And that's where we had this giant leap in computing, because now software is a lot quicker to write, even though they were hampered by this problem. Okay, today we don't even have this problem, because now when we write software, and we're gonna see this when we get into it, I'm gonna talk about the different ways of storing integers and where that came from. But as computer programmers today, we don't spend a whole lot of time wondering or worrying about how much memory is this going to take up. Because in general, unless we have a very, very, very specialized problem we're solving, we have more memory than our program will ever need. So, you know, our modern programming languages have multiple ways of storing whole numbers. We have bytes, we have shorts, we have ints, we have longs, and we'll talk about this next time. This is kind of where we'll start off. But in fact, I'll even start the slide for that. All right, so we have bytes, short, int, long. So these are 4 different ways of storing what are called signed whole numbers. Positive and negative whole numbers, no decimal point. Now the reality is so if we're going to store the number 75, 75 will fit inside of a byte or a short or an int or a long. If we roll back to a programmer back when memory was super, super expensive, if we only needed to store the number 75, we would purposely choose a byte, because that is the smallest footprint of memory that the programming language allowed us to grab to hold the kind of value I'm about to hold, a whole number, but it still contained it. All right. Kind of like having, if you had, organizational boxes at home, and you went and found the perfect size. Oh, it's like Tupperware when you're having leftovers, right? You go and find the perfect piece of Tupperware that will hold whatever your leftovers are, rather than bringing out the giant casserole dish with the lid that you bring to your church functions, right? And you put your little scoop of mashed potatoes there in the corner and throw it in the fridge, right? We get the perfect size bucket now, right? Just because we're thinking about, the limited space in the refrigerator. Well, years and years and years ago, you would have chosen a byte to store that number. Today, if you're a programmer, and you're going to store a signed whole number, you store it in an int. And if it doesn't fit in there, you put it in a long. If it doesn't fit in there, well, then you got to look at the object-oriented options beyond that. And we'll talk about those things. But this guy is never used anymore. Modern day programmers will never use shorts. Bytes only get used when we're like doing video streaming and stuff, because things tend to stream in bite-sized chunks. It's just it's compatible with the problem we're solving. It has nothing to do with storage capacity stuff. All right. So we'll start here next time. And we're going to get into variables and asking questions. And so we're going to learn next time. We're going to probably hit you with an upfront. Here's how to define a variable. Here's how to ask a question. Here's how to write a loop in C++. And then we'll work backwards and fill in the gaps so you see the starting point as quick as possible. This will match up your C++ skills to that slide we talked about, how do human beings solve problems. Memory, asking questions, repetition. All right. I will see everybody on Thursday.
That's good.